All right, we'll start from this slide, but we'll actually go back and do the last thing in section 5.1. But before we do that, let me give you these announcements. I think probably the most important announcement is this one. First, it's going to be a question. How many have done the student course evaluations? All right, a few of you have. Thank you very much. Please, everybody, they won't, okay, you may not think this influences you, and probably to some extent it doesn't directly, but you can still have a really big influence on the college and on students who come after you. But the student course evaluations, one of the things that we are going to have in the next few years, that's why I said you'll probably already be gone, maybe, before they come, a SACS accreditation visit. It's a reaccreditation visit. CJ? Yeah. Oh, I'm sorry. Justin, got you. I'm just trying to find you here. All right, sorry about my hearing. Okay, now, we have coming up within the next few years a SACS reaccreditation visit when the college gets accredited. We generally never have any problems because administration runs a pretty tight ship on this. We have one of the premier SACS people who does a lot of SACS visits, and she's been doing it for years and years and years on staff here, and she makes sure we're in line. But one thing she cannot control is what you do. Okay. And student course evaluations, they are beginning to look more and more at participation in this. And in the past, historically, it's sort of been moving this way. We've been trending downward, so only like 20 to 30% of the students are actually responding. They're looking for 80% response. So please, people, please do the student course evaluations. It's important for us as a college, but it's also important for the next students coming after you. Because if you do good, solid evaluations of us and of the college, we then have a chance to say, whoa, we need to improve on this, But right now, we're getting very little feedback historically. I get fairly good, I think, in most of my classes, just from interaction with you. But you see, the people who are in offices and stuff like this is their major form of feedback, So please, don't just do it for the class, the course. Do it also for if they ask you any others, like registration process, library, food service, whatever they do. Ask you, please do a good evaluation. I'm not saying give us good evaluation, but do an honest, thorough evaluation office. That helps us more than, just saying, oh, they're off, whatever. So please do an evaluation. Please, folks, do the evaluations. All right, number 2, this one isn't quite as crucial as this one, but just to let you know, normally on Fridays I have office hours on the Birmingham campus, 7:45 to 11:45. This Friday, not. I've got an infusion coming up this Friday, and so I will not be on campus Friday. I will be at the Kirkland Clinic basically all day long. So I will not be there on Friday. All right, I can't think of anything else except what's coming up 2 weeks from tomorrow. Say again? 2 weeks from tomorrow. Election Day. Do not forget it. I'm not going to tell you who to vote for or what to do, but I want you to vote. I want you to get into a habit of voting every time the polls are open. That's where we have the most influence. And believe me, there are special interests that do not want you voting. They want their candidate in, so you please get out there and vote. If you're not registered, today's the last day you can register and still vote in Tuesday, the 12th election. You register now. After the day, you can vote in upcoming elections. But if you register, you can go online, alabamavotes.gov. I think it's what the website is, alabamavotes.gov. Yeah, right. Okay. So please, folks, vote 2 weeks from tomorrow. Don't forget. Please remember to vote. And tell all your family members, all your relatives, all your neighbors, everybody, get out the vote, folks. Please, it's important. One of the most important elections for a long, long time. All right, let me see if I can find a little white space here that I can work a problem on. That may be the best I can do. So let's do example 5 on the top of page 248, chapter 5, section 5.1. Okay? Express this. Let me get my pen set up. Again, the computer is awfully slow today. Okay, here we go. Express this. A to the minus 1 plus b to the minus 2 as a single fraction involving positive exponents only. Now, they gave you a couple of hints there saying the same thing. What would you do to express this expression as a single fraction with positive exponents only? What would be your first step? Okay, yeah. The a to the minus 1 is the same as 1 over a. Is that what you meant? Good. Plus 1 over b squared. Perfect. Now that's still two fractions. You got the positive exponent part, but you still have two fractions. So how can you write that as a single fraction? Adding or subtracting fractional forms, what must you get? Common denominator. Very good. And what would be the common denominator between those two? AB squared. Perfect. AB squared. Now, how do you get this A to be an AB squared? What did you have to do? Multiply by B squared. So what did you got to do to the numerator? Multiply it by B squared. So that new numerator becomes B squared. Okay? Now, what did you have to do to this denominator, to this one, to get it to become this one? B squared to become AB squared. Multiply by A. So what must you do? Multiply the numerator by A as well. Okay? Now we have common denominators, so let's put everything over AB squared. And what do we do with the numerators? Add them, exactly. So that becomes B squared plus A, or A plus B squared. Either way you write it is fine. Now we've done what they said. We wrote it as a single fraction with only positive exponents. Every exponent is positive. Okay? Does that make sense? All right, good deal. And in the book, that's exactly the answer they got. They didn't do A plus B squared. That would have been perfectly fine, but they chose to leave it this form. Perfectly good. There is a little concept quiz here. They're all true-false questions. I would definitely do them. Good little exercise, practice, because then just flip over one page and you'll get the answers, so you can do them and check them really easily. If you can't get the answer there, giving there, and can't figure it out from their answer, then please ask that, because those are the concepts that your next quiz and test will be focusing on. All right, let's do homework exercises then. Problems, any of the odds 1 through 41. A whole passel and a half of them. So I do one of every type. Some of those simple ones at the beginning, some that have multiplications in them, some raising powers to powers, some products of different bases. You know, do some of each of those. Okay. Number 41, a little bit similar to the one we just did, not quite. Okay, then do any of the odds 43 to 61, and do some of each of those types, and then do any of the odds 63 to 73, and then finally, these are the ones like the one we just did, any of the odds 75 to 83. Any questions on that? All right. So I'm going to first clear the screen. That's not the one I want. Let's see. Yeah, there it is. Got to get used to my old method. The other computer didn't let me do it this way, so got to get back to the... All right. We're continuing Chapter 5, Exponents and Radicals. We know what exponents are. What are radicals? What are radicals? We'll get to them in a bit. So hang on to the thought. We'll get there in a bit. Right now, we're still evaluating roots of numbers, or will be evaluating roots of numbers. We'll express a radical there. We'll get to it in the second part of this one in simplest radical form. We'll talk about 3 rules there. We will rationalize the denominator to simplify radicals, and we'll apply some radicals, applications of radicals. So, we know about exponents. That's raising the number to a power. To square a number means it raises it to the second power, okay? That is to use the number as a factor twice. So 4 squared is what? Say again? 16. 4 times 4, which is 16. 10 squared would be 100. That's 10 times 10, which is 100. What is 1/2 squared? Say again? I can't hear. 1/4. It's 1/2 times 1/2, which of course is 1 times 1 is 1, 2 times 2 is 4. What is -3 squared? 9, not -9, because it's -3 times -3. You use that as a factor twice, but when you multiply a negative by a negative, it becomes a positive. So that's a positive 9. Now, if that would have been an odd exponent with a negative inside here, it would be a negative answer. Even exponent with a negative inside is going to be a positive. Even exponent with a positive inside will still be positive. Anything with a positive inside will be positive. Okay. The square root now of a number is one of its 2 equal factors. Thus, you can go backwards in this. The square root of 16 would be 4. Or at least one of the square roots of 16 will be 4. Therein opens a little bit of a problem for us, because a square root of number is one of its 2 equal factors. -4 times -4 also gives you 16. Okay? Certainly positive 4 does, but -4 would be. Thus 4 is the square root of 16, because 4 times 4 is 16, but also -4 times -4 is 16. What would be square root of 100? 10 or -10. Square root of 1/4? 1/2 or -1/2. Square root of 9? 3 or -3. Either one. Both of those are square roots. Now, this is the first, I think, incident that we've gotten in mathematics where you do an operation, you get 2 possible answers. Most of the time, you only have 1 possible answer. Here we have more than 1. Okay? Well, we actually, that's not quite true, but it's pretty close. Likewise, -4 is the square root of 16, because -4 times -4 is also 16. In general, if A is a square root of B, if and only if A squared is equal to B. So, if you say A equals square root of B, another way to write that same equation, square both sides, and you get A squared is equal to the square of square root of B. Square undoes the square root, you just get B. All right. The following generalizations are a direct consequence of that statement. We've already hinted at this. Here they put it in writing. Every positive real number has 2 square roots. One is positive, one is negative. They are the opposites of each other. Plus or minus 4, plus or minus 3, whatever. Negative real numbers, however, have no real number square roots at all, because any real number except 0 is positive when you square it, and 0 squared is still 0. And here they just said that the square root of 0 is 0. Okay? So every positive real number has two square roots, one positive, one negative. Every negative real number has absolutely no real square roots. If you go into the complex number system, yeah, you can find square roots there, but not in the real number system. And the square root of 0 is 0. Okay, well, that means any real numbers, positive, negative, I'm sorry, not positive, negative, positive, fractions, decimals, radicals, rational, irrational, as long as they're positive, you have two square roots, but if they're negative, no real square roots. All right, so this symbol here is called the radical sign. Now, quite often we'll shorten it and just call it the radical, okay? But that's actually called the radical sign. It's used to designate the non-negative or the principal square root. If you want the negative square root, then you put a minus sign in front of it. That tells you take the principal square root and negate it, because that will also be a square root. The number under the radical sign, that doesn't have one, but what would be there, is called the radicand. That's the name for it. The entire expression, such as the square root of 16, where 16 would be the radicand, this is the radical sign, this is now technically what we call the radical. Okay? Square root of 16 would be called the radical. And we know that the square root of 16 going this way is 4, because this indicates or means principal square root or primary square root, okay? Meaning the positive square root. If you want the negative, put a minus sign in front of it, okay? Square root of 0 is 0. We saw that on the previous thing. 0 has only one square root. It's the only number that has only one square root. Positive, well, it's not a positive number anyway. Square root of negative 4 is not a real number, and square root negative the square. I was going to say negative square root of negative 4 is not a real number. We're not dealing with the i's in this case at all. Okay? Got a general idea there? Now, something else I said they aren't really focusing on, but square roots undo squares, squares undo square roots. Those are inverse functions of each other. You'll later name them that way. Just like addition undoes subtraction, subtraction undoes addition. Multiplication undoes division, division undoes multiplication. Square roots undo squaring, like squaring undoes square roots. All right, in general, the following definition is useful. If A is greater than or equal to 0, and B is greater than or equal to 0, then the square root of B is A, if and only if, and again, we square both sides, A squared is equal to, and you square a square root, you just get what's under there, B. Okay, because the squaring function undoes the square root. A is called the principal square root of B. Principal square root, because we said A was positive, B of course has to be positive, take the square root of it, and you're taking the positive square root of that, if and only if that is true. Principal square root. Now, that's squaring. Cubing introduces another set of rules, basically. To cube a number, just like squaring a number, means raising it to a power, the third power. That is to use the number as a factor 3 times. So what is 2 cubed? Say again? 8. 2 times 2 times 2, 3 times. That would be 8. 2 times 2 is 4 times 2 is 8. What is 4 cubed? 64. You're reading my sleep, okay? Yeah, 4 times 4 times 4. That would be 64. That's what it means to cube a number. Now here's the interesting part. Not that it's not interesting. Well, we'll get to that in a minute. What is 2/3 cubed? 8 over 27. You cube the numerator, you cube the denominator. 8/27. But here's the one that's different. -8. Because when you, and I've mentioned this before, when you raise a negative number to an odd exponent, it comes out negative. Okay? Meaning when you cube a number, when you square a number, it's always going to be positive, never negative. When you cube a number, if you cube a positive number, it'll be positive. Cube a negative number, it'll be negative. Remember that. This one you can have a negative number if you cube a negative number. The cube root of a number is one of its 3 equal factors. Thus, 2 is the square root, is the cube root of 8, because 2 times 2 times 2 is 8. Is minus 2 a cube root of 8? No, because minus 2 cubed is negative 8. In fact, 2 is the only real number that is the cube root of 8. For instance, taking the square root of a positive number, you always get 2 possible, one positive, one negative. Take the cube root of a number, only get 1. Okay? There are 2 others, but they're complex. We're not doing those. Okay? Furthermore, negative 2 is the cube root of negative 8, so you can take the cube root of a negative number, because negative 2 times negative 2 times negative 2 is negative 8. In fact, negative 2 is the only real number that is the cube root of negative 8. There are 2 others, but they're complex. They're not real. Okay. Make sense? All right. So the differences between square roots and cube roots. Square roots, you can't take the square root of a negative number in the real number system. Cube roots, you can. When you square, take a square root of a positive number, you get 2 possible ones. One's positive and negative. Take a cube root of either number, you only get 1. Only 1. Okay. In general, A is the cube root of B. That would be A is equal to the cube root of B. I haven't shown us how to write that yet, but we're going to get to it soon. If and only if A cubed is equal to B. The following generalizations are a direct consequence of that statement. Every positive real number has 1 and only 1 positive real cube root. Positive real cube root. Every negative real number has 1 and only 1 negative real number cube root. And the cube root of 0 is 0. They love putting that in there. It's pretty important, right? Doesn't say much. All right. Technically, this is what I've been saying. Every non-zero real number has 3 cube roots, but only one of them is real. The other 2 are classified as complex or imaginary numbers. We're not going there. Here is the symbol for a cube root. It looks just like the square root symbol, except it will have a little 3. This little 3 here is called the index. Okay. Now I want to point something out to you. Everywhere in algebra up till right now, if you didn't see a number, you assumed it to be 1. If you had x plus 3, what do you assume the coefficient of x is? 1. Okay? If you saw negative x plus 3, what would you assume the coefficient of x was? Negative 1. You put a 1 in there anytime you notice it. If you see x plus 3, what's the exponent for x? 1. Okay? Okay? So any time up to now, if you didn't see a coefficient, didn't see an exponent, didn't see something, you assumed it's the coefficient or the exponent or whatever is 1. Here is one difference. If you see a radical sign and you don't see a number, guess what you assume that number is? 2. That would be a square root. We don't do the first root of anything. The first root of something is itself. So we never even bother to write it. So if you don't see a number inside a radical, you assume it's a square root. If you do see a number in there, that's called the index, and that tells you which root you're doing. Okay? So, with that in mind, what's the cube root of 8? 2. Is that plus or minus 2? No. Only 1. Okay? And that's 2. What's the cube root of negative 8? Can you do it? Can you do it? Yes. Cube root you can do, square root you cannot. Can't take the square root of a negative number, you can't take the cube root of a negative number. What would that be? Negative 2. How about the cube root of 1 over 27? 1 over 3. Cube root of negative 1 over 27. Negative 1 over 3. Now, I don't know if I asked you to do this before, okay? I probably didn't ask you to, but, boy, when you leave the board with ink on it over a long weekend, it's hard to erase. Okay. Yeah, I have it up here, but then it's years. Let me see what I can do. Just for funsies, I think we did this before. Write down the numbers. 0. Ooh, that's terrible. Okay, let's see. This is it. 0, 1, 2, 3, 4. We did this, you remember? And you can go on more than that if you want to. Let's call this n, the number. Then n squared would be what? 0 squared is 0, 1 squared is 2 squared is 3 squared, 4 squared, 5 squared, 6 squared, 7 36. Right? 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100. You can go further if you want to. But then let's do n cubed. And if you write your table like this, the real easy way to do it is just multiply n times n squared, and you'll get it. So 0 times 0 is 0, 1 times 1 is, 2 times 4 is, 3 times 9 is, 27, 4 times 16, 64, 5 times 25, 125, and these get harder after this. This is 216, I think it is, and generally I don't remember the ones past that. But you can do the table, it's really easy to do. Just multiply 6 times 6 is 36, carry 3, 18 and 3 is 21. You can do those till the cows come home. But that way you'll help you recognize what are the perfect cubes squared. And later we'll come to fourth roots, fourths and fifths and stuff. After a while they get too hard to see. And that may be why you have calculators, okay? All right. Any questions on that? Okay. So in general, here's the following definition. Very close to what we just said. The cube root of number, the cube root of b, that's how you read this. The little index of 3 means cube root. That's the root symbol, the radical symbol. Okay? The cube root of b is a, if and only if, you cube this side, you cube that side. A cubed is equal to. Cube undoes the cube root, that leaves you with a negative. Okay? In this definition, if b is a positive number, then a is a positive number. If b is a negative number, then a, the cube root, is also a negative number. That doesn't work for square roots, but it does work for cube roots. Okay? The number a is called the principal cube root of b, or simply the cube root of b. I see no reason to put principal in there because we only got one. So why bother even saying principal? With square roots, you got 2. If it's a positive radicand, you'll always have 2 square roots. The principal one is the positive one. Okay, p positive, principal. Okay. The concept of a root can be extended to 4th, 5th, 6th, in general, nth roots. The 435th root of something. I'm not going to do those. I'm not interested in those, but you could do it. The nth root of b, that would be this radical symbol with a little n as the index. The nth root of b would be as inside the radical, the radicand, is a, if and only if, raise this to the nth power, a to the nth, raise the nth root of b to the nth power. The roots and the radicals cancel out, and you just get b. That's what it means. Now, let's take that another step. With that in mind, nth root, that kind of thing, if n is any positive, even positive integer, 2, 4, 6, 8, 10, 12, any of those positive even integers, this statement's true. Every positive real number has exactly 2 real nth roots. One is positive, one negative. So the nth root, the fourth root of 16, we didn't write that in there, but if you did it in 4, that'd be 0, 1, and then on this case, just multiply 2 times the 8, not all of them together. 2 times 8 would be 16. 2 to the fourth power is 16, so the fourth root of that would be 16. So it has 2 real roots. The fourth root to 16 would be either plus 2 or minus 2. Plus 2 would be the principal or positive square nth root, fourth root. Negative 2 would be the negative nth root. So they're both the fourth roots of 16. Negative real numbers do not have real, negative real numbers do not have real nth roots when n is an even integer. You can't have the fourth roots, no real fourth roots of negative 16. You just can't do it. Because anytime you raise a number to the fourth power, it's whatever the number is, it's going to come out positive. So you cannot have a fourth root of negative 16. But, on the other hand, if n is an odd positive integer greater than 1, we don't usually do the first root, so only greater than 1, that's 3, 5, 7, 9, any odd number there. The following statements are true. Every real number has exactly one real nth root, if n is odd. The real nth root of a positive number is always positive. For example, the fifth root of 32, here you would do another column here. You do the n4 and n5. You do 2 times 8 would be 16. 2 times 16 would be 32. So that's how you get that one. That would be positive 2, and the nth real root of a negative number is negative, and you have fifth root of negative 32 is negative. Does that make sense? All right. Good deal. Now, this symbol, just like before, the radical symbol will, any number or a indicator for a number, like n, indicates the nth principal root. Okay? So if you have an even here and a positive number there, that is indicating the principal nth root. If you have a odd number here and either positive or negative there, then that's going to be the only, because odd numbers only have one nth root. You don't have two, so principal is not necessary to say there, but you can say it. To complete our terminology, the n in the radical, now I've already told you this, the nth root of b is called the index of the radical. So if n is equal to 2, we commonly don't, we just write it with the square root symbol. We usually don't do it. So if you ever see the radical without an index, you understand that to be the square root. Again, this is the one and perhaps only place that if you don't see a number there, you assume it's a 2 rather than a 1. That's for radicals. The following chart will help summarize this information with respect to the nth root of b. They're sort of beating this to death, aren't they? Where n is a positive integer greater than 1. Okay? If n is even, that's the first thing you look at. If that n is even, then the nth root of b has to be positive. B has to be positive. And the nth root of b, if you don't have a sign in front, you assume it's the positive real number. Always the principal, if you don't see the sign in front. Okay? If b is 0, then the nth root of b is 0, because the nth root of 0 is 0. But now remember, if n is even and b is negative, no real numbers. You cannot take an even root of a negative number. You can't do it. No real number. If n is odd and b is positive, then the nth root of b is a positive real number, whatever that nth root is. Nth root of 0 is 0, always, and the nth root of an odd, if n is odd and b is negative, the nth root of b is then a negative real number, always. These two, if the b coming in, if this is an odd sorry, if this one's n is odd, b is positive coming in, the answer is going to be positive. If b is negative coming in, the answer is going to be negative. For even roots, b has to be positive. And then, if you just have that symbol there, you understand the principle of positive nth root. Okay, here are some examples. The fourth root of 81. 3, okay? That's because 3 times 3 is? 9 times 3 is? 27 times 3 again is? 81. Now, is that how I do it every time? No. I say the fourth root of 81. Well, let's take the square root first. What's the square root of 81? 9. And then take the square root again. Square of the square is a fourth. And that's 3. Okay. Makes it easier. And because this is positive, that's got to be positive. Fifth root of 32. Well, I said that wrong. Because there's no minus sign in front, that has to be positive. Because that was even root. What's the fifth root of 32? 2. Okay, very good. Odd here, if that's positive, this is positive. Fifth root of negative 32. Can you do it? Yes. Why? It's an odd index. And what would that be? Negative 32. For odd indexes, whatever the sign is here, that's going to be the sign on the outside. How about the fourth root of negative 16? Fourth root of negative 16. Nope. Even index, you can never take the even index of a negative number. Because if you went the other way, raising a negative number to an even power, always positive. So you cannot do that. Not a real number. Okay? So any real number except 0 is positive when raised to a fourth power. Okay? 0 is 0 when it's raised to the fourth power. So again, you can take this table and expand it to the fourth, the fifth, the sixth, as many as you want to. We're not going to go much past fourth, I don't think. No fifth. They do fifth. And frankly, it's only going to be the smaller numbers we go that high because they get really big really fast. Okay. But your calculators can do them. So learn how to do that. If you don't know, come see me and we'll figure it out. I can't teach a calculator because you may have different kinds of calculator. They may use different symbology. Everybody got it? Or still working? All right. While people are still getting this down, let's go over what's going to be happening the next 2 weeks. We have class this week and next week. The following week is finals week. So, we're going to get as far as we can in Chapter 5. Hopefully, I think we'll get far enough to at least have a quiz on it. Okay? It doesn't look likely we're going to have time to have a test on Chapter 5. Sorry about that. But what we're going to do, that last day of class, which will be not the final, the last day of class, will be 1 week from this coming Wednesday. On that day, I'm going to return all your quizzes and all your tests to you. So that means that's the last possible time. Tuesday before that, 1 week from tomorrow, it's the last time you can make up any quizzes or tests. So please get these things done soon. Sooner the better, so I can return them to you sooner, hopefully. Okay? Number 2, that day, that Wednesday, I will not teach any more from the book. I will use those review sheets that I passed out to you early in the term, and we'll go over any questions you have on any of those. Because some of the things there we haven't gotten to. We've gotten to the basics, okay? The stuff we haven't gotten to, I think you'll find is fairly easy to pick up, okay? So that's what we're going to do. And then, on Monday, finals week, which is normally when you would have your final, if you want to have another review day, I will be glad to continue that. If you don't want the second review day, you don't have to take it. I'll find someone to practice the test and put you in a separate room. Unless all of you want to do it, then I'll not need anybody. But I want to give you a chance for a second review day. Since we haven't finished all the material, I want you to be able to go through any questions we don't have time for that Wednesday. The last Wednesday, we'll have Monday. And then after that, anytime you want to come in and take the final, you can. Doesn't have to be a Monday or Wednesday. It's any day that's convenient to you, any time that's convenient to you. Okay? But leave at least 2 hours to do it. Don't come in, well, I only got an hour now, can I get started? Well, no. Let's set aside 2 hours and come in and take it. Okay? All right. So, everybody had all that. Oh, you didn't? Okay. I thought all my talking there, you'd have a chance to get it all done. Sorry. You probably stopped and listened to me. Good for you. Okay? Glad you were listening. Any questions on what I just said? I can't hear you. Final will be normal. It's scheduled for Monday, the whatever. Let's see, 2 weeks from today, it would be whatever that turns out to be. Yeah, that sounds right. Yeah. Because next week would be the first Monday in December, 11th would be the second Monday, I think. Whatever it turns out being, that's the day it's scheduled for. However, I will do another review day for you. We have an hour and 50 minutes that day, not an hour and 15. So we have more time to review then. And then any time after that, you can take the final. If you want to come in Wednesday, I'll be here Wednesday. Okay? Now, I'll tell you then what my final schedule will be, so you can know when I'm in finals and when I'm not. I will be in a final no, I won't. No, I won't be in a final that Wednesday at 9. So anytime you want to come in, you can. But then after that, you work it around yours. Everybody got this now? Okay. So the following property is a direct consequence of definition 5.5, and this is what I was saying to you earlier. If you have an nth root and raise that to an nth power, the power undoes the root, and you wind up with what's inside. They sort of wipe each other out, and you wind up with B. Like if you have 7 plus 3, 7 plus 3, 10, minus 3, 7. You're back where you started with. Adding and subtracting undoes each other. 7 times 3, 21, divided by 3, 7. You end up where you were. 7 raised to the third, okay, let's not do that one. Let's do 27 to the third root of 27 is, third root of 27, 3. 3 cubed is 27. So whatever you had in here, you wind up with that. N is any positive integer greater than 1. This is true. Okay? There's one thing that's not quite true about that. As long as that's defined. I'll put it that way. Okay. Now, the nth root of b to the n, this time, you're starting with b, raising it to a power, and then taking the root of that, the same root, that also gives you b. So let's start with 27 again, and do the, let's start with 3 this time. 3 cubed is 27, and the cube root of 27 is 3. So whatever you started with at 3, you wind up with 3. This is true for any positive integer greater than 1 if b is greater than or equal to 0. Okay? If n is an odd number, odd positive integer greater than 1 if b is less than 0. Okay. That all says the same thing we were just saying before. They really say it strangely. Usually you can tell by looking at the numbers what they'll turn out being. So, because the radical expressions in part 1 and 2 of that, 5.3, are both equal to b, by the transitive property, they're equal to each other. So in other words, here's what they're saying. The nth root of b to the n is the same as the nth root of b raised to the n. Okay. Now, frankly, to me, this makes the arithmetic is usually easier if you do this. Take the root first, because you see, if you raise a number to a power, it gets huge, and then to take the nth root of that is more difficult. If you take the nth root of a number, it makes it smaller in general, and then that small number raised to a power, and it's easier to do. So this is usually the best way to do. Take the root first, then raise it to a power. Even if it's given to you like that, change it to this and do it that way. Okay? So the following examples demonstrate that use. Okay, what is the square root of 1/44 squared? 1/44, okay? And you don't have to go through this. You see, a square root undoes a square, okay? But if you do it the way they suggest here, that would be the square root of 1/44, and then square it. What's the square root of 1/44? 12, and 12 squared is 1/44. This one, the cube root of 64 cubed is it's just 64, because the cube root undoes the cube. You don't have to turn around and do this. You can. The cube root of 64 is 4. 4 cubed is 64. But when you see it like this, you can just remove the root and the power if they're the same. If the index is the same as the exponent, just remove it. It's when if you didn't have this, well, that would, let's continue. We'll see a better example. Okay. Cube root of -8 cubed. Anybody? Cube root of -8 cubed. It's just -8. And you don't have to go through all that. Is it? The fourth root of 16 to the fourth is 16. Perfect. Okay. Now, let's use some examples to lead to the next useful property of radicals. So notice we're having lots and lots of properties. Here's the deal here. The square root of 4 times 9, you can do it two ways. You could either multiply these two together. That would give you 36. Square root of 36 is 6. But an easier way is do the root first. Okay, and that's what they do. Okay? But the other way to do, since both of these are perfect squares, just do the square root of 4 times the square root of 9. What's the square root of 4? 2. Square root of 9. And 2 times 3 is 6. This keeps the number smaller. Okay? Same thing here. Square root of 16 times 25. Do I want to multiply 16 times 25? No. Okay? And then if I got it, I probably wouldn't know what the square root was. Let's say, yeah, I would. 16 times 25 is 400. Square root of that is 20. But much easier to do the square root of 16, which is 4 times the square root of 25, which is, and 4 times 5 is 20. That's a lot easier to do than that. How about cube root of 8 times 27? I don't want to do it. Okay? That would be the cube root of 216. If I hadn't written that on the board, I probably wouldn't know it. So what I'll do is cube root of 8 is 2. Cube root of 27 is 3. And 2 times 3 is 6. So yeah, you get the same answer. How about the cube root of -8 times 27? Well, you couldn't multiply it through like we did here and get that answer. But far easier, cube root of -8 is cube root of -8, -2, cube root of 27, 3, -2 times 3 is -6. That's the easier way to go. If they're perfect cubes and perfect squares and perfect whatever, that's easy. Guess what? Most of the time life is not that nice to you. Okay, they won't be perfect roots. Okay? In general, we can state the following properties. If you have the nth root of a product of two different bases, then it's the nth root of the first base times the nth root of the second. So the root of a product is the product of their roots. Okay, that's an easy way to say it. Now that is when the nth root of B and the nth root of C are real numbers. So if B or C happen to be negative numbers and that n was a even root, can't do it. You cannot do it. Okay, that rule doesn't apply. The nth root of a product is equal to the product of the nth roots. Just what I said. Wow. That whole group there, and we didn't have a single example. I mean, we had some that they showed you the answers, and I covered them so we could do it, but not a single example. Now, here we will have some examples coming up real quickly. We'll be expressing a radical in its simplest radical form. Okay? There are three rules that we're going to go by. So let's start with this. The definition of an nth root, along with one of those properties back there, 5.4, provides the basis of changing radicals into simplest radical form. The concept of simplest radical form takes on additional meaning as we encounter more complicated expressions, but for now it simply means that the radicand is not to contain any perfect powers of the index. We'll do another couple rules to it later, but that's what we're meaning. Okay? Now, there's a couple ways you can do this. I'll start with the way they're suggesting, and then I'll show you another way. When you're doing the, you tell me, what does it say? What does that expression mean? It's a simple answer. It's not anything complicated. Square root of 8. Okay? Since you're dealing with square roots, you look at the 8 and say, do I see any perfect squares hiding in 8? Since this is a square root, any perfect squares hiding in 8? Say again? Say again? 4 is a perfect square, isn't it? Yeah, 8's not, but 4 is, and that's hiding in there. So what I'll do is I'll rewrite this as the square root of 4. Actually, I'll do it this way. 4 times 2. Isn't that 8? Okay, and by the last rule, we said that's the same as the square root of 4 times the square root of 2, right? And what's the square root of 4? 2. So this is 2 root 2. That's the simplest form for that. Now, it may not look to you like it's simpler, but it really is. Okay? So that's the first rule for writing a radical in simplest form. Find any perfect powers of whatever the root is there. If they're in there, lurking in there, get them out. Okay? How about 45? Does that, what does this mean? Square root of 45. You see any perfect squares hiding in 45? Think down your list. Never do 1. There's always 1 in there. So and don't do 0 if 0 can't be in there, okay? Any perfect squares hiding in there? 9, yeah. 9's a perfect square, right? So this will be the square root of 9 times what? 5. And that will be the square root of 9 times the square root of 5, right? What's the square root of 9? 3 root 5. There's written in simplest form. Okay? Whoa, the cube root of 24. See any perfect cubes hiding in 24? Say again? I can't hear. I don't think so. The cube root of 27 is 3. That's why I say, write that list out for you. Do any of those perfect squares there, perfect cubes there, hide in 24? Here's a perfect cube. Again, don't do 0 and 1. Will 8 go into 24? Yes, it will. There we have it. So that would be the cube root of what? 8 times 3, right? And that would be the cube root of 8 times the cube root of 3. And what is the cube root of 8? 2 times the cube root of 3. Now, I think I heard what he just said there. He went straight to he skipped this step here. And once you get used to it, yeah, I skip it too. I'm trying to show you this is how we got here. How about the cube root of 54? Second? Okay. The trouble is, yeah, okay. 8 is a perfect cube. Will 8 go into 54? 8 will go into 56, but not 54. If that had been 56, 8 would have been the 1. Look at your cubes over there. Any of those go into that? 27 will, for sure. And that would be what? 3 times, and what's left when 27 goes into 54? 2 times the cube root of 2. No cube there. Now, right there twice. Once on this step and once on that step. And this is the error I make more frequently than any others. When I'm doing other roots with indexes there, I get so fired up about getting that part right, I forget to put my cube, my 3 there, that index there. Don't forget to. That gives you a wrong answer. So you got the 3 out, remember that's the cube root of 2. Now I'll give you another way to do this. The book doesn't show this, at least not now. It may a little bit later. But I'm going to show you another way to do this. Okay? Square root of 8 is also the square root of, guess what we're going to do now? Prime factorization. What's the smallest prime number that will go into 8? 2. 2 times what? 4. Is 4 a prime number? No. What is the smallest prime number will go into 4? 2 times what? 2. All right. Now, you've done a prime factorization. Now, what you do here is look at the index. And what is the index here? 2. Find a pair of numbers in there. Same number, and there you have it. That pair right there. 2 times 2. That is the square root of 2 squared, right? Which is just going to be, pull that number out, 2, and you're left with root 2. Okay? Pull this one completely on the outside, but not the multiplied, because the square root of that would be 2. Let's do the same thing with square root of 45. What's the smallest prime number will go into 45? Say again? 5 will go into it. How many times? 9. Smallest prime number will go into 9. 3 times what? 3. Okay? Now, I would have said started with 3, but it's okay if you started with 5. I saw that too. And here we have a square root, the index 2. Here we have a pair of numbers. Right? Pull that out, 3 root 5. Same answer we got before. Let's do the cube root of 24. The cube root. Now, I'm going to ask you for what's the smallest prime number go into 24? 2. 2 times what? Is 12 prime? No. What's the smallest prime number go into 12? 2 times what? 6. Is 6 prime? No. What's the smallest prime number go into 6? 2 times what? 3. That 3 is prime. Okay? You look at your index. 3, you have to find a triple of numbers. Same number. There it is. Pull out the 2, and you're left with the cube root of 3. Same answer as before, and you didn't have to look for lurking primes. If you do prime factorization, that'll show them to you. Okay? So if you prefer it this way, and for really big numbers that I don't recognize if a prime number could be hiding in there, this is how I would do it. Let's do it for 54. That would be the cube root of, smallest prime number going to 54. 2 times what? 27. Smallest prime number is 27 prime. No. Smallest prime number going to 27? 3 times what? And is 9 a prime number? No. Smallest prime number going to 9? 3 times what? And 3 is a prime number. There we have it. You got an index of 3. You found a triple of 3s. Pull that on the outside, and you're left with the cube root of 2. That's the other way to do it. If you don't want to look for that perfect nth root hiding in there, do your prime factorizations. I'll give it to you. Just remember, what you pull out are the index, the number of repeated powers that is equal to your index. Okay. Unfortunately, we just ran out of time. I'm sorry. We have plenty of room. Okay. That was example 1. Let me very quickly show you their solution here. And I think you'll see it's the same as ours. And that would be the cube root of 8 is, square root of 8 is square root of 4 times 2, which is square root of 4 times square root of 2, which is 2 root 2. Square root of 45, square root of 9 times 5, square root of 9 times is 3. Square root of cube root of 24 is cube root of 8 times cube root of 3. That's 2 times root 3. And cube root of 54 is cube root of 27. Okay, got it. All right, we'll start next time with, let me give you homework exercises. Any of the odds 1 through 19. Any of the odds 21 through, we'll just stop at 27. We'll pick up the rest of those next time. Good deal. Any questions? Sorry, we ran out of time. Mark where we are now. Okay. All right, you too. See you Wednesday.